So, like I said in the last video, we want to look at some application now. And the application is often called optimization. And this happens all the time in businesses, in engineering, in all kinds of things where you want to maximize something or you want to minimize something. So classic is we want to maximize profit, we want to maximize revenue, we want to minimize cost. So I thought we'd do an example that is sort of very hands-on. You can actually go get some paper and do this, kind of play with this as we make the video if you want to. I guess I did, for whatever reason, I did choose a paper size that you probably don't have. I'm going to pretend like this is 11 by 11, but just you can just cut your paper into an 8 by 8 and then pretend that it's 11 by 11, and it works out the same. So this is going to be a square piece of paper. I've drawn mine a little bit rectangular, I guess. Whatever, it's close enough. And we're going to chop the same little square out of each corner. So let's label these. I'm going to call the length of that x. So each one of these lengths is x. And then we're going to fold the flaps up. And so when I do that, I'm going to get this open box. And so the question is simply to find x where the volume of the resulting box is maximized. I want maximum volume. So this is a great little problem that's going to help guide us into some other problems as well. So the strategy here is very much what you'll need for other problems. So first thing you want to do is you want to try to write down some formulas. See if you can model the situation. So the question is, when you chop length x, what's the volume that you get? And so let's realize that in this case, the volume V is, well, the volume is going to be the area of the base times the height. The area of the base, this is actually square, so these are the same sides. So it's the full 11 minus x, so it's 11 minus 2x squared. And then the height is just x. So the volume is x times 11 minus 2x squared. You won't always get the equation that you want to optimize in one variable. We'll see that in forthcoming problems, but in this case you do. Next thing that you want to do is ask yourself, are there any restrictions on my variables? And it might be more than just x itself. In this case it is actually. So for starters, are there restrictions on x? And you should realize, yes, there are. It would not make sense for x to be a negative number. I don't know what that would mean, but it'd be very strange. Try and draw that if you can. Whoa. So x can't be negative. Actually, we don't really want x equals to 0. X equals 0 makes perfect sense mathematically. You get a box with 0 height, and so the volume is 0. That really, we want to avoid that. So it's clear from this problem that you want x strictly bigger than 0. If you're paying attention, you know that 11 minus 2x is this length right here, and that has to be positive as well. So x has to be bigger than 0, and 11 minus 2x has to be bigger than 0. Let's actually solve that inequality, and we get 11 has to be bigger than 2x. So I'm going to flip it and write x has to be less than 11 halves. So the point is, my problem requires x to be bigger than 0 but less than 11 halves. Now, hopefully you've just noticed that I'm working with this function. This function is continuous. And I'm working on the open interval 0 to 11 halves. The point is it's open. It's not closed and bounded. Now, you could get around that in this case and say, yeah, but I know what happens at 0, so you can include those. That's fine. But I want to show you how the extreme value theorem doesn't apply technically to this open interval. And I want to show you how we can still confirm that our solution really is the absolute max that we want without knowing from the extreme value theorem that there is a max. So in summary, key takeaway here, this function is continuous, but we're looking at an open interval. So we don't actually know that there's a maximum using the extreme value theorem. That's okay. Here's what we're going to do. We're going to go ahead and compute the derivative. So I'm going to work it out and just factor it. There's lots of ways. You can use the product rule, or you can expand this out and then refactor whatever. When you compute the derivative, you're going to get 11 minus 2x, and you're going to get 11 minus 6x. We're interested in where is the derivative equal to 0. And so my critical points in this case are 11 halves. Let's say x equals 11 halves, and x equals 11 over 6. We've already seen 11 halves is not really an option. If you plug that in, we're going to get out 0 for our volume, which we really don't want. So 11 over 6 is the key. Then I'm going to put all the interesting points on my number line for v prime. And I want you to realize that you want to put everything. So I've got to be between 0 and 11 halves. And here's my point, 11, 6 in the middle. Now, I'm going to go ahead and label the intervals. I'm only interested in intervals inside of my interval. My interval is going from 0 to 11 halves. So I'm going to label this side and this side. And if you'll do that, you're going to get a plus here. Plug in something between 0 and 11 sixes. You're going to get a plus and then a minus there. You don't have to graph the whole function. You just need to see this. And now you realize something. You realize that your function, your derivative, is increasing on the left. It's increasing from 0 to 11 sixths. Then it's decreasing down to 11 halves. Now, it turns out it actually goes on and it increases to infinity. This is v that I'm talking about. If you wanted to graph the function, it's going to do something like this, and then it's going to bounce. Whoops, that's not what I wanted to do. It's going to do something like this, maximum, then it's going to come down and it's going to bounce and shoot up forever. You don't need to know the graph. Okay, it's easy enough to know that if I have a local max here, but the point is, if I'm always increasing on this side, and then I'm always decreasing on that side, that has to be not just a local max, but an extreme, an absolute max as well. This is an extreme value. So at this point, we can say that V has an absolute extrema of V of 11 over 6 equals 121 over 9, which, by the way, that's roughly 13.44 on this interval 0 to 11 halves. Now let's actually answer the question we were asked, i.e., maximum volume occurs when x equals 11 over 6. And the key reasoning here, the reason that I know that's an maximum volume is because my function is increasing, then it's decreasing, and that means this has to be not just a local max, but an absolute max on that interval. All right, so we'll stop this video here. We'll go on and do 2 more of these, and then we'll call it a lecture series.